Okay, so here's the certain problems I promise you are going to be on the test. One of those is going to be when you take like a 20-gram mass or something like that and you hook it on the end of the pulley and it's going to go like this, okay? So here's what's going to happen. I got a 20-gram mass on the end of this string. So what's the first skill you have to be able to do to use this value? What do you have to be able to do?
Tie a knot.
Find the,
Kilograms.
which is 20 divided by 1,000 is
0.02?
0.02.
Yeah, I knew that.
So, yeah, there you go. And 0.02 times 9.8 gets you 0.196. So let's just call this about 0.2 newtons. So the first thing you've got to be able to do is find the weight. London, what did you do?
He stuck 2 magnets.
Tell me you didn't put those 2 magnets together. London? London? You keep them completely separate. I'm going to put them on either side of your ears and just smash them together. You know why I don't teach freshmen? I did. Okay. And it's always boys. Always. Girls, love y'all to death. Guys, you're a pain. Okay. So this weighs 0.196 newtons. So I'm going to put this on the end. Initially, we're going to assume that this is a frictionless surface. We're going to start with the idea that force net equals force applied plus force opposing. Put down that magnet.
Did you put them together?
You do realize I have to write the test. Do you really want me to be irate when I write the test for this class? Thank you. Ladies, I'm going to give you like, there's going to be like the guy version of the test and the girl version.
Perfect.
Guy's version is going to be written in Latin. Hope you can translate. Okay, so your girl's going to be like, here's the force, here's the mass, find the acceleration. Okay. All right.
Please.
All right. So, but here's the story. I got a 0.196 Newton force acting on them. So that's the only force available to make this thing move. If it's frictionless, how am I going to determine the acceleration? What am I going to divide by? The mass on the end, or the mass on the cart, or the combined mass?
Combined.
Always, always, always divide by the combined mass of the system. So I'm going to take this 0.02, add it to the mass of the cart. I'm going to take that force of 0.196 newtons, divide it, boom, there's going to be my theoretical acceleration. Gravity's pulling down on this, but the track is providing a normal force to balance it out. So now I want to change it up a little bit. So now I want to put a couple of blocks underneath the ramp. So now I'm going to take the tension off the string. I'm going to let go of it. Now what's going to happen? 1G.
It accelerates
Why?
because the force parallel is pulling it down.
Okay, so I've got the force parallel acting down. Jackson, which direction does the force parallel always act?
Down.
Down. When I let go of this string, I promise you I'm not going to let go of the string and all of a sudden it's going to start moving towards me. Okay? If that happens, there's something weird going on. Promise you, we could do this lab. Guaranteed home run results. Hey, put it on an incline plane and let go of it 10 times. Every time, what's going to happen? Down the inclined plane. But now I want to change it up a little bit. So now, when I let go of this thing, I've got that dragging it down, but then I'm going to put, let's go with a 50-gram mass on the end of it. So now I'm going to put a 50-gram mass on the end of it, and now I'm going to let go of it. So which force is bigger? The weight from the 50-gram mass or the force parallel? Add it. How do you know?
Because it's going up.
Yeah, that's the direction that it moves. So the gravity mafia pulling down on the 50-gram mass, whoop, steady, is bigger than the force parallel. That's why it goes in that direction. However, if I put a 10-gram mass on the end of it and do that exact same thing, now when I do that, it accelerates down the inclined plane. So in one situation, it accelerates up the inclined plane. The other situation, it accelerates down the inclined plane.
That was
I'm
not.
not even anywhere near the table, bro.
You reached out and kicked it.
That was it.
Oh, the boys' test just got harder. So,
I'm not part of that group.
okay. So, when I changed this, did I change the force parallel? Matty Hill, you shake your head no. Why?
Because the weight is the applied force, not the force parallel.
Beautiful. Whatever I do here has no bearing on that force parallel. What's the only thing, what are the only two things that determines that force parallel? London.
Force, gravity, and the mass of the
Beautiful. Okay? So that force parallel is determined by the weight and the angle, right?
Yeah.
Steeper I make it, what's going to happen to my force parallel? It's going to get bigger. So right now when I do this, hook that up, I do this, I let go of it, force parallel is bigger. Do you think by much? Yeah, because it barely accelerates down. So now we're going to make it very complicated. So now I'm going to put that 50-gram mass on the end. Okay, so now I got that action. Then I'm going to take this and put the magnet in there. So now when I put that magnet in there, I'm going to let go of it. So what are the three forces? Now I have three forces involved. I got the 50-gram mass on the end of the string. I got the force parallel acting down. I also, what's the third force now? The magnet. Which direction does the magnet always act relative to motion? Opposite direction. It's like friction. It always acts in the opposite direction. So when I let go of this thing, let me get that lined up. So here's what you want to do, and you're going to have a problem like this. If you hand in the test tomorrow, and you haven't worked a problem that involves a weight on the end of the string, an inclined plane, and a magnet, you have done something horribly wrong. Okay? It's going to be the last page, top problem. It's going to be these three things. So when I let go of this, start with this idea. Just make this observation. What's the direction of the acceleration? Uphill or downhill? Uphill. On the problem, I'm going to tell you, 1G, you're not going to get the vote. Uphill is going to be defined as positive. Downhill is going to be defined as a negative value. I'm going to tell you that straight up. Okay? Uphill is positive, downhill is negative. So if I let go of this thing and I see it accelerate up the hill, what does the value of my net force have to be?
Positive.
Positive. If I let go of it and it begins to accelerate down the hill, my net force has to be a...
Negative.
Start with that idea. When you get to this problem, read it. Oh, great, it accelerates down the hill. I better have a negative net force. I better have a negative acceleration. Okay? If I say it accelerates up the hill, better make sure everything's a positive value. Start with that idea. Now, I have three forces involved. I've got this, this is going to be my applied force. Which direction is that force going to act on that cart? Of it. Up. So I'm going to make this a positive value. So now, which direction is my force parallel going to act? Down. Force parallel always going to act down. You know this is going to be an applied force making it go up. The weight on the end of the string has to be a positive value. Your force parallel has to be a...
Negative.
The only thing I can determine is the sign of the magnet. So if I put it like this, and let go of it, and it accelerates up the incline like this, what's the direction of the force from the magnet? Down, because it's the opposite direction of motion. Now, if I do this differently, and I put a 10-gram mass on the end of this thing, now when I let go of it, it's going to accelerate down the inclined plane. Not much, but let's make that a little bit more extreme. Now, if I put another block on the end of that, what did I do to my force parallel? Increased it, because it's a steeper angle. Now when I let go of it, I get an acceleration down the inclined plane. Is my force parallel still acting down the inclined plane? Yes. Nick, what's the direction from this? Up or from the weight on the end of the string? Is that acting up or down? Up. The weight on the end of the string is never going to push this thing down the inclined plane. The weight on the end of the string always acts up. The force parallel always acts down. Now, if I do this and I let go of it, what's the direction from the force from the magnet? Up or down? Up, because it's in the opposite direction of motion. So literally, I promise you, there's going to be three forces. There's going to be weight on the end of the string. Make that go up. Make the force parallel go down. And I'm going to tell you which direction, and I'm going to give you this value. I'm going to give you the force from the magnet. I'm going to tell you it's 0.1 newtons, it's 0.2, whatever that is. What you have to decide in the context of the problem is which direction that's going to act. If it accelerates down, you make the force be positive. If it accelerates up, you make the force from the magnet be negative. Got it? Good? Back we go.